Hello, everybody. So today we're going to continue our discussion in Chapter 2, Section 4. And what we're going to talk about is a couple different things. The first thing is going to be what is called the step function. Now, in a previous video, you saw me show you a little bit about what the step function was. It literally looks like a set of steps. But I want to go into a little bit more detail as to why the function looks like the way it does. So functions whose graphs resemble a set of stair steps are also known as step functions. The most famous of the step functions is called the greatest integer function. And the first thing that I want you to see is how it's denoted. What you see me highlighted right there is that they're kind of like a bold-faced bracket with an x in between them. So the x is your variable, but the brackets themselves are basically if you draw two kind of spines and then draw the bracket. That's how you would draw that. But that bold-faced bracket is what indicates that this is called the greatest integer function. And what that means is the greatest integer is function is going to take the largest whole part out of the number that is inside there. Where it's pretty easy to understand, except for whenever you get into the negative numbers, and that's a little tricky. So I'm going to skip the first two there and just look at this. So if I put the number 1/10 in there, 1/10 does not have a whole part to it. It is only a fraction. So it rounds it down. And the easiest way to think about is this function always rounds numbers down. So 1/10 would be rounded down to 0. Now you have 1.5 in the next one, and normally when we round, 0.5 would round up, but in this case we're going to round down to 1. So as you can see, it's taking the greatest whole part out of the number. Even 1.9. That number is going to round down to 1 when it's in the greatest integer function, because it's taking the biggest whole part. So it's always rounding down. Now, when we get into negative numbers, it gets a little trickier. -1 is an integer, so it doesn't do anything to the number -1. But if I look at the number -1/2, as an example, I'm going to show you on a number line how we can think about this. So we have this number line at 0. -1/2 would occur right here between 0 and 1. Now remember, down on a number line is to the left. So this -1/2 would actually get rounded down to the number 1. So the greatest integer function of -1/2 would round down to -1. So remember, for the negatives, just think on the number line and then move to the left. And you can see that it gives us a function that looks like a set of stairs. Now, we've already talked about what the domain and range of this function is. The domain, you can put any number you want in there, and as you look at these stair steps, they're always covering left to right all of the x values. So all of the x values left and right are covered. But the y values are not all covered. You can see there's these gaps in between the numbers. And the reason being is that you only get outputs that are integers. So as you can see here, -4, -3, -2, -1, 0, 1. Those are only integers, which is why it's called the greatest integer function. So the first example that I'm going to show you is example 2. It says evaluate the function when x equals -1, when x equals 2, and x equals 3/2. So we're going to start by taking our function that you can see that they gave us. F of x is equal to the greatest integer function x plus 1, and we're going to substitute each of those x values in. The first number we're going to substitute is -1. And when I do that, -1 is not changed. -1 is an integer. You don't need to round it. So it stays -1. And then you have +1, which then gives me 0. Okay, so that one was pretty easy because the function didn't do anything to the number. In a similar fashion, whenever we substitute the number 2 in, you can see the greatest integer function. When we substitute 2 in, it does nothing to the number 2 because it is already an integer. It doesn't need to be turned into an integer. So 2 stays 2, 2 plus 1 is 3. The last x value that they wanted us to try is 3 halves. Now, when I substitute 3 halves in, 3 halves is not an integer. That is a rational number. Integers are negatives and positive whole numbers, right? So if you take the whole numbers, which is 0, 1, 2, 3, 4, and you also make them negative, that's the integers. So you can see we have 3 halves right here. Remember, 3 halves is 1.5 or 1.5. This function always rounds numbers down. So 1.5 would round down to 1. And you can see that's why the 1 gets replaced right there. So you have 1 plus 1. And so then the answer would be 2. So when you plug in 3 halves, you get 2 out. And that would be the graph of the greatest integer function x and then plus 1. And what I would like you to notice is the whole set of stairs were shifted up by 1. That is what this plus 1 does right here. This takes the whole graph and bumps it up 1 step. So if you look at the original one up here, you can see that the function starts at the origin and then goes to the right to 1. Whereas this other one, because it had that plus 1, it does not start at the origin. It starts up at 1 because this step came up from here and was shifted up 1 because of the plus 1. Okay, so the next thing that we need to discuss is what a piecewise defined function is. Now, I said in a previous video that there's another name that some teachers will refer to these as. They will call them split domain functions. Split domain functions are probably a more descriptive name of the function, but most textbooks and most teachers will call these piecewise defined functions. And the easiest way for me to describe what a piecewise defined function is to simply think of those collages that you've made in various classes where you've cut a whole bunch of pages out of a magazine and had to put them together to make a poster. That's kind of what these are. We're cutting pieces of a function, and then we're going to put those two pieces together to form a new one. Now, I really kind of just showed you how to evaluate these in the previous video. Today, I'm going to show you how we would actually graph these. Okay, so I'm gonna start by showing you what this piecewise defined function would look like if it were just two separate functions. And this is not how I would go about normally graphing these, but I'm doing it this way so you understand why the graph looks like it does. So you can see I'm going to have two different coordinate planes at first, okay? So I'm drawing my first one, drawing my second one. I'm going to graph the 2x plus 3 over here, and then I'm going to graph the negative x plus 4 over here. So 2x plus 3 would start at 3. And I'm going to get my red. And then it would go up 2 over 1 to the next point, which would put me right about there. And so then when I drew my graph, it would look something like this. And I'm going to try to draw that line a little bit straighter. There, like that. So there's the graph of 2x plus 3. Now the next one, the negative x plus 4, we're going to do that in a similar way. We're going to go ahead and go up 4. And let's use purple for this one. So I'm going to go up 4, put a dot. Then I'm going to go down 1 over 1 and put another dot. And I'm going to graph this line right here. Oops. Now, I've got these two graphs, and these two graphs are each of the graphs separately. But what we need to do is we need to cut these in half, and we're going to cut them based on what these functions say. So we're going to cut these right down through 1 right here. And then I'm going to cut these right down through 1. And what I want you to see is that the first one, this 2x plus 3, is less than or equal to 1. That we only want this part, the part that is less than or equal to 1. So I'm going to completely erase all of the graph to the right of that, all of this is going to go away. All this, because I do not want anything that is greater than 1. I only want the stuff that is less than or equal to 1. Now, in the second graph, you can see that I want x is greater than 1. Okay, so what that means is I only want this part of the graph, the part that's greater than 1. I do not want anything to the left of that graph. So all of this is going to get erased. All of this. Okay, now once that's erased, what we're actually going to do now is we're going to take this part of the graph and I'm going to put it together with this part of the graph. Whoops, I messed up. Hold on 1 second. I didn't erase all of this. This part needs to be erased as well. And now whenever I cut this out, I'm going to put these two things together just like that. And I get a new graph. Now, the last thing to notice is the purple part, this purple part, which is this. The dot should be an open dot. So I'm going to go ahead and put an open dot right there, and I'm going to leave the red one as a closed dot. And so that's what we did. So we took part of one graph and we took the part of the other graph, and then we put the two graphs together. And by putting them together, we get pieces of each of the graphs, which is why it's called a piecewise defined function. And you can see we can do this on the graphing calculator, but the graphing calculator does not put the dots on the graph. So you'll have to know what those are on your own. So I'm going to show you how to do another one, but I'm going to do it this time not by taking each piece, but just by graphing it. Okay, so what we are going to do is we are going to graph the following piecewise defined functions. So this is how I would normally explain this. I would not graph both of them separately and then take the two chunks away. I would put them in one graph right away like this. So the first thing we're going to do is we're going to cue in on where the split is. And you can see the split is happening at 2. So I am going to go to 2, and I'm going to put a vertical line right down through the number 2. And we know that that's where the split in our graph is occurring. Okay. The next thing that I'm going to do is I'm going to get my colors picked for each of the graphs. So I'm going to graph this one in blue, and I'm going to graph this one in, let's go with green. Okay, so what you need to understand, though, is where each piece is going to be graphed. This first piece in blue is graphed when x is less than or equal to 2. So this is -1/2 x minus 6. That's where this is going to get graphed. It's to the left of that border. The x squared plus 5 is getting graphed to the right of that border. Okay, so each part is going to get graphed, but only on its side of that border, which is at 2. So let's graph the easy one first. The easy one is going to be the linear graph. So we need to go down 6. And I'm going to graph that one in blue. So I'm going to go down 6. So I'm going to put a dot. And then I could go down 1 over 1. Now, if I go down 1 over 1 one more time, notice the dot for this one would be a closed dot because it's equal. So I would put a closed dot right there. And then I'm going to draw my line. Now, notice I'm only drawing my line on the side that that equation belongs on, which is to the left of the dashed line. It does not get graphed to the right. Now, the second one gets graphed to the right of that number 2. So I'm going to make, since that's a quadratic equation, I'm just going to make a table. And I'm going to pick numbers that are 2 and bigger. So I'm going to pick the number 2, and then I'm going to do 3 and 4, and that will be enough points. So when I plug 2 into that equation, 2 squared is 4 plus 5 is 9. 3 squared is 9 plus 5 is 14. And 4 squared is 16 plus 5 is 21. Okay, so these points are going to get graphed over here. Notice I picked my x values. These x values were picked based on picking x's that were greater than 2. I did pick 2, but you have to remember that this is going to be an open dot. So when I go, that's a lot of hash marks, but you can see that we're going to be all the way up here for an open dot. And I'm kind of running out of room. And then the graph, the parabola is going to go up even higher like that. But that's what your parabola would look like, just like that. So there's your graph of your piecewise defined function. So you can see each part has to be graphed on the correct side of the line. And again, you can see this is what we would do on a graphing calculator if you would do that, but the graphing calculator doesn't include the open and the closed dots. Okay. Now it says, I'm going to show you how to graph them on the graphing calculator. So it's pretty simple. And like I said, the biggest thing with the graphing calculator is you have to know what the dots are, because your graphing calculator will not do the dots for you. So let me show you how this works. You hit y equals, clear out anything that might be in there. You type in your equation, in this case, -1/2x and -6. But here's the key part. This is how you put the restriction in. You need to put a comma, and then you use a set of parentheses, and you write this restriction. In this case, x is less than or equal to 2. X, and then you've got to go to second test to get the signs that you need. And the test is right above the math. And there's your less than or equal to, and you would write 2. Close your parentheses. And I misspoke here. It's not a comma. It's a divided by sign that you need to put in there. Okay. The second one is going to be x squared and then plus 5. And once again, you're going to hit divided by and put a set of parentheses and then write your restriction. In this case, x has to be greater than, which is 3, 2. So you can see what I have in there now. I have the -1/2 x minus 6, and then divided by x is less than or equal to 2. And then I have the x squared plus 5 divided by x is greater than 2. And now when I hit zoom 6, so everybody's looking at the same window, you can see there is the linear part of my graph. And way up at the top, you can barely see it, is the quadratic. I am going to make my window, instead of having the y max 10, I'll make the y max 20. So you can see that a little bit better. So there's the linear graph. It stops right at 2, and then the parabola takes over and goes up. It doesn't draw this border line, although I do like you to have it in there when you're drawing by hand. Also notice that the dots are missing because the calculator won't do the dots. So that's how you graph a piecewise defined function, and that's how you graph it on your graphing calculator. So if you guys have any more questions on this, as always, feel free to email me or ask during our live Google Meets. So there's a few problems I'd like you to work on. Have a good day.